You know, if you've ever worked with a spreadsheet, played a game of chess, or even just looked at a map in a video game, well, you've already got the basic idea of a 2D array. In C programming, they're the tool we use to build these awesome grid-like structures to organize all kinds of data. So, here's our roadmap. We're going to start with what a matrix even is. Then we'll get our hands dirty reading and writing data to it. After that, we're tackling two classic exam questions you are almost guaranteed to see: adding and transposing matrices. And to finish up, we'll go over the common mistakes, so you can avoid those headaches. All right, first things first, let's really lock down the foundation. What exactly is a 2D array? You'll hear it called a matrix all the time, both in programming and in math, so let's get clear on it. At its heart, a 2D array is really just an array of arrays. I like to think of it like a filing cabinet, where each drawer has its own set of folders inside. It's this structure that makes it absolutely perfect for representing anything with two dimensions, whether that's the pixels on your screen or the coordinates on a map. This slide is so cool because it shows you how we can take an abstract idea, like the connections in that network on the left, and turn it into a super organized grid on the right. See, each row and column stands for a point, and the number in the cell tells us if those points are connected. It's a really clever way to turn complex relationships into simple data a computer can chew on. And here's the magic spell to bring that grid to life in your C code. This one line is you telling the compiler, hey, set aside some memory for me in a grid shape. You just have to tell it what kind of data you're storing, give your grid a name, and then define its size with the number of rows and columns. Easy as that. Okay, so we know how to create a matrix. Now for the really fun part, the most fundamental skill of all, actually getting in there to access and mess with the data inside it. So just imagine you've got this big 10 by 10 grid. That's 100 cells. You are definitely not going to write 100 lines of code just to read everything. So what's the elegant, programmer-approved way to visit every single cell without going crazy? The answer is nested loops. This is the absolute classic go-to tool for this exact job. The outer loop is in charge of the rows, right? It starts at the top. Then, for each row, the inner loop kicks in and just zips across every single column in that row. Once it's done, the outer loop bumps us down to the next row, and the inner loop does its thing all over again. It's a beautiful, systematic way to hit every single cell. All right, let's dive into the kind of problem you've been waiting for. This is something you're almost certainly going to see on an exam or in a technical interview: adding two matrices together. Now hold on. Before you even think about writing a single loop, there's one golden rule you can't ever forget. To add two matrices, they have to be the exact same size. Same number of rows, same number of columns. You just can't add a 2 by 3 to a 4 by 5. It doesn't make any sense. So the first thing your code should do is check that they match. Once you've confirmed they're the same size, the algorithm itself is actually super simple. You use those nested loops we just talked about to visit the same cell in both matrices at the same time. Let's say the cell at row I and column J. You grab the value from matrix A, add it to the value from matrix B, and you pop that sum right into the same spot in your new result matrix. You just do that over and over for every cell. Okay, let's tackle another super common operation you're going to need to master. This time, we're basically flipping a matrix on its side to find its transpose. What does that really mean? Well, all you're doing is taking the rows from the original matrix and turning them into the columns of a new one. The first row becomes the first column, the second row becomes the second column, and you just keep going. This is a really key operation in stuff like computer graphics and data analysis. And the code to do this is brilliantly simple. Check it out. As you loop through the original matrix, using I for your rows and J for your columns, you take that element and put it into the new transpose matrix. But here's the trick. You swap the indices. The element from original IJ goes into transpose JI. That tiny little swap of I and J is where all the magic happens. Okay, we've covered the what, the how, and a couple of key operations. Now let's wrap this up by looking at some of the classic mistakes that programmers make, especially when they're starting out. Knowing these will save you a ton of debugging time. The biggest takeaway here? You have to be meticulous with your numbers. First, always remember that C starts counting from 0, not 1. So a 3-row matrix has indices 0, 1, and 2. If you try to access index 3, your program is going to crash. That's an out-of-bounds error. And this is exactly why you have to double, even triple check your loop conditions.
It should pretty much always be I less than rows, not I less than equal to rows. These little off by 1 errors are, I swear, the source of most array bugs.
So let's do a quick recap. We figured out that a 2D array is just a simple grid for our data. We learned that nested loops are our absolute best friend for working with that data. And then we saw how even complex-sounding things like matrix addition and transposing are really just built on that same simple looping logic. And now you've got a solid handle on how to build and manage these powerful data grids. The possibilities from here are, well, pretty much endless. The logic you learned today is the foundation for everything from a simple tic-tac-toe game to complex algorithms that find the best path through a maze. So the only real question left is, what are you going to build first?